Thank you for everybody for joining today. I am Ayub. I have recently graduated with a degree in geomatics and surveying engineering. In this year, code of first edition, I am working on compression of geospatial data with varying information density. I am very fortunate to have the guidance and supervision of Hauke, Milan, Juanjo, and Miha to wrote this project. So for my presentation, we will begin by introducing compression, why we need it, and what is it exactly. Then we will delve into the bitwise real information content-based compression, which promises exciting possibilities, followed by a presentation of the challenge I have been working for 2 months now. And lastly, I will conclude by sharing some preliminary results. So the exponential growth of data across multiple fields has created a demand for efficient data management. And according to the ECMWF website, an astonishing 200 terabytes of atmospheric data are being added daily to the archive. To address this challenge, compression, also known as source coding or bitrate reduction, plays a crucial role. It involves code information using fewer bits than the original representation. And by compressing data, we can achieve several benefits, such as saving disk space, reducing the bandwidth usage, and improving overall system performance. And the compression involves a trade-off between the precision, that is the information content, the size, usually the disk space, and the compression speed. The goal is to achieve optimal results in all aspects. However, in practice, the aim is to strike a balance that suits the requirements of the application and the available resources. So before getting further, I want to remind you of how floating numbers are stored in memory. It is actually similar to scientific notation, but is in base 2 with the small catch in the exponent. So the first bit is reserved for the sign. If it's a 0, the number is the positive. If it's none, as in this example, the number is negative. The next set of bits represent the biased exponent. It controls how far and in which direction to move the decimal point in the fraction. And the exponent is represented in a biased form to allow for positive and negative exponents. The bias is a function of number of bits reserved for the exponent. And the biased exponent is then used to calculate the actual exponent value, 2 to the power of 4 in this case. The remaining bits represent the mantissa, also known as the significand or fraction. And these bits represent the fractional portion of the number in binary form. So for the bitwise real information content-based compression, it is done as follows. A first step is the bitwise information, that is the mutual information between the bits is calculated. So a bit position contains more real information. The stronger the statistical dependence to the adjacent bits it is. Then we keep only the bits with real information and discarding the bits with the false information. After that, we apply our lossless compression. To visualize these steps, I have taken this graphic from this paper of Clover and al. So we work with the gridded data from Cartesian, curvilinear, or unstructured grids, and we utilize the binary representation for efficient storage. So, and the second step is analyzing the mutual information of adjacent bits position. And we identify the key bits that are the significant bits that preserves most of our real information. And finally, we remove the false information bits by rounding them to 0, ensuring effective compression. Another example for clarification. So we can start with a one-dimensional bit stream of data. Using the concept of mutual information, we identify and retain only the significant bits that are in the middle in black here. And then the compression can be thought of something like this. And by applying this approach, we compress the data from 160 bits down to 60 bits. To illustrate this further, I will share an example with code. So for this, we will be using xbitinfo, which is an X-array wrapper around the bit information GL to retrieve and apply bit rounding from within Python. The package intends to present an easy pipeline to compress datasets based on the real information content. And also to note that bit information GL was developed during the summer code edition of the years 2020 and 2021. And the dataset used for this example is the 2-meter temperature in Kelvin from the ERA 5 dataset. And you can get it from the Copernicus Climate Data Store. And the data type is float 32. So the first thing is getting the information content per bit. As we can see, the first bits contain no real information. So in the last portion of this image. And then the values start relatively high and start decreasing near the end. For the second step is we get the key bits. And the key bits, as I mentioned earlier, refers to the number of bits from the Matissa that are necessary to retain most of the real information. In this particular case, the key bits value is calculated to 8 bits. This value is then utilized to round the original data using the XR bit round. And then we can go to the compression. So the original size is stated as 64 megabytes, which can normally be compressed to approximately 34 megabytes, resulting in a compression ratio of around 2. However, when compressing the bit rounded data, it results in a size of 4.1 megabytes, achieving a compression ratio of approximately 15. And here in this example, I am showing water vapor from the CAMS dataset, specific humidity compressed in the longitudinal dimension. And we observe a transition from preserving 100% of the information on the left to 83 on the right. The purpose of this demonstration is to showcase the impact of this method of compression. And as you can see in the right-hand side, the visual representation appear very pixelated. However, this highlights that we can easily preserve around 100% of information without sacrificing any crucial details within the dataset. The challenge I am working on is a continuity of the compression method using bitwise real information content that has been developed during last edition of 2020 and 2021 by Miel and Clover. And this year I am working on the development of an information density adapting compression by implementing compression and bit information retrieval on a chunk basis, analyzing the information density of climate variables across time and space, and studying the optimal chunk size depending on different features like hurricanes. So for my preliminary results, I will be showing in this analysis. So chunks possess key bits values that are approximately similar to the key bits value of the entire dataset, which is the expected outcome. However, we are working on developing a metric to assess whether chunky provides superior results. And in this analysis, however, as a part of our ongoing work, we are actively developing a metric to evaluate this performance. And this metric will help us assess whether chunking provides this result in terms of information retention and compression efficiency compared to analyzing the datasets as a whole. And for this surface pressure, similar observation can be made for this variable as well. And in the second, like in the third step from our goals, we have examined the impact of chunking on specific features as hurricanes. In this case of the ERA 5 data, we analyzed the hurricane. So we did not observe any significant differences in the variance of key bits values for the chunk where the hurricane occurred. However, we suspect that for higher resolution data and smaller chunks, we may observe variation in key bits value. So further investigation is required to confirm this hypothesis. And similar findings can be observed also for the mean sea level pressure variable, as mentioned in the previous slide. And for a summary, the bitwise real information context-based compression can be done by calculating the bitwise information and getting the key bits, discarding the bits without real information, and then doing the compression. And chunking can enhance this compression. And for the next step, we will explore higher resolution data sets and smaller chunks. And we will analyze the information density of climate variables and the effects of chunking, as most of the code is ready for now. And this is my last slide. I'm happy to take any question if there are any. Thank you.
Thank you. Thank you very much, Gio, for your presentation. Very, very nice. You have a lot of results so far. So we don't know if there is any question specific
no, I don't
for you
see at the moment.
So what is the big challenge from this project? This is a follow-up of this is the third year of this compression data project. What has been your big challenge? Because you are only one person as participant, as developer.
Yeah, so actually it went really smooth. So the one thing that was not very much a challenge, but just the learning curve. So at first I didn't know much about the bitwise information compression and that. So the learning curve was a little bit steep, but yeah, it's all going smooth. And I want to thank again all the mentors that are doing tremendous work. Yeah.
Yeah, but it has been a learning experience as well so far.
Yeah.
So perfect. Thank you.